There are some quantities that we have studied in the previous lectures that do not depend on viscosity. So, for instance, some of them could be the drag coefficient, the lift coefficient, the pressure coefficient, or the shock angles like beta and delta. These quantities, for instance, these coefficients here, these force coefficients at high Mach numbers, they have very little dependency on the viscosity. And these angles here, beta and delta for the shock waves, they can be obtained from the invisible theory. So that the viscosity is negligible in these coefficients simplifies greatly the problem. However, there are situations in which we cannot afford neglecting viscosity. For instance, if we have a surface and this surface is at some temperature Tw, and then there is a stream above it that has a temperature T infinity. In order for us to calculate the heat flux, or for instance to calculate also the shear stress on the wall, these quantities, the shear stress and the heat flux, they depend on the viscosity for the shear stress and for the heat flux on the thermal conductivity. So one needs to bring the viscosity and the thermal conductivity into the picture, and the invisible theory is no longer valid. Well, the role of viscosity too has to do a lot with altitude. Just to summarize here one typical mission profile of a hypersonic vehicle. So if this is the surface of the Earth and this is the edge of space, a reentry trajectory like this is going to cross the edge of space. And then it's going to have to traverse all this layer of atmosphere. This atmospheric layer here, right, this entire atmosphere has a thickness of approximately 100 kilometers. Those are the kilometers, that's the distance that is relevant for aerodynamics. The atmosphere actually goes beyond this altitude, but it is such a low density gas that it is irrelevant for the forces that one has to calculate and for the heat fluxes that one has to calculate. This long distance entails large variations of certain properties. For instance, if one talks here about the density, right? The density can be written as a function of the altitude as sea level density rho naught multiplied by the exponential of minus beta multiplied by the altitude z. This rho naught here can be approximated as the density at sea level, which is about 1.2 kilograms per meter cube. Whereas this coefficient here, beta, this prefactor here, beta, has the units of the inverse of an altitude. And it is given by, the inverse of beta is given by this number here, 6.7 kilometers. So this number here, 1 over beta, is called a scale height. So it is important to notice, for instance, that when one evaluates this profile at 6.7 kilometers of altitude, one obtains that rho is equal to rho naught multiplied by the inverse of the exponential. So this will be at an altitude of 1 over beta, which will be 6.7 kilometers. So at 6.7 kilometers, the density is the sea level density multiplied by the exponential to the minus 1. This number here is about 0.37, which means that at 6.7 kilometers, the density has already decreased by 63%. And at altitudes larger than 6.7 kilometers, the decrease is even larger. So this density decreases exponentially with altitude. And the first e-folding of the density occurs relatively soon, at 6.7 kilometers. Remember that here we are talking about altitudes that are of the order of 100 kilometers. So just after 6.7 kilometers, we already have a decrease in the density of about 67%. So this can be seen in the slide. In the slide, you have a figure that shows the altitude in kilometers in the vertical axis, and in the horizontal axis, you have the density. So you have a solid line that is taken by a database that is useful for calculations that is called the US Standard Atmosphere. And the dashed line is the formula that I just wrote on the blackboard with those two calibrated parameters, the density at sea level and the scale height. Well, in the red region that you have in that figure is that's the region that matters for hypersonics. So it's up to altitudes of about 90 kilometers. So this black line that you have on the screen is, as I said, obtained from a database that is called the US Standard Atmosphere, that you can Google it and download it, and for instance obtain the properties at any altitude in the terrestrial atmosphere. But this is a sort of an average number for the density based on measurements and based on calculations. So in a realistic atmosphere, the density may depart from those standard values that the US Standard Atmosphere gives you. So here, for instance, in this screen, you have 3 panels of 3 space shuttle missions, the STS-2, STS-4, and STS-6. In the vertical axis, you have the altitude, and in the horizontal axis, you have a ratio of densities. That ratio of densities is the ratio of a density that was measured by the space shuttle and a reference density that is given by the standard atmosphere. So it is perhaps useful to see that those measurements of the density in the space shuttle, they were actually derived from the acceleration, because if one writes the second Newton's law for the reentry in a spacecraft, one is going to have that the mass of the spacecraft multiplied by its acceleration. This is going to be equal to a force. This force in general is going to be composed by lift and drag, but in general it's going to be of a form 1/2 multiplied by rho infinity multiplied by a force coefficient and multiplied by an area and multiplied by a velocity squared. So by measuring the acceleration, one can actually post-calculate the density, and that's what it was done in those plots that you see in the screen. Most importantly, if you look at the deviations of the density, well, they tend to be of the order of 20%, right? 20% deviations from the values that are observed or collected in the US Standard Atmosphere. And those variations, they tend to happen along altitudes that, for instance, if you look at the first figure on the left, right, you see that there is a large decrease of about 20% in the first peak, right? And that decrease happens along, let's say, 20 kilofeet, 20,000 feet. Well, if you think about it, that, for instance, that variation, if you have a spacecraft that it is re-entering, a space capsule, and this space capsule is going to be moving at velocities that are comparable to the first cosmic velocity. So it's going to be moving at velocities that are of the order of 40 kilofeet per second or so. The fact that one has variations of density of 20% along an altitude interval, which is about 20 kilofeet. If you think about it, what happens is that over around 1 second, because these 20 and 40 are more or less the same, in about 1 second, the density field around the spacecraft is changing by a 20%. So just trying to give you some idea if you had to calculate the numerical simulation of subject to those variations. You would take the capsule, and then around the spacecraft, the density will have to vary by 20% in just 1 second, right? So the boundary conditions would actually change. And those boundary conditions will be changing correspondingly to that peak with a frequency of about 1 Hz. That's, for instance, the widest peak that you have seen here. If we go back to the screen. So if you look at high frequency peaks, those high frequency peaks are going to generate variations of density in times that are much shorter around the spacecraft. So those high frequency peaks, they actually correspond to variations of the order of kilohertz, 100 to 1 kilohertz. So one will have, in order to address those high frequency peaks, you will be calculating the motion of this spacecraft, but then around the density field will be changing in frequencies of about 100 to 1 kilohertz. This frequency or that characteristic time needs to be compared with the characteristic flow residence time around the capsule. And this characteristic residence time around the capsule tends to be of the order of 100 to 10, from 10 to 100 microseconds. So this is to say that these frequencies, they can get to compete with the residence time around the spacecraft. So one needs to be careful with those atmospheric fluctuations. Well, not only the density varies exponentially, but if we look at the screen, the pressure also varies exponentially with altitude. And there you can see, for instance, the pressure in solid lines and the density in dashed lines. And you can see that there is also a difference by a factor of 10 to the 5 or so in the pressure just across the red layer. That is the one that matters for hypersonics. The fact that the pressure and the density follow each other well is because the temperature does not vary that much across the red region. This can be seen in the next slide. So in the next slide, you have the altitude in the vertical axis and the temperature in the horizontal axis. And there one can distinguish different regions in the plot that actually match the thermal lapse. By thermal lapse, what I mean is the slope of the temperature is 0. So there you have some parts of the graph that have a 0 temperature slope, and those are called 0 thermal lapses, or in the case of the troposphere, it's called the tropopause. The next one is the stratopause, and the next one is the mesopause. Well, there in the screen you can see different layers. The first layer is the troposphere. The troposphere goes from sea level till 11 kilometers of altitude. It is within that layer that you have most of the weather in the planet, right? You have most of the clouds are there. You have also airliners flying through that layer. For instance, one picture that you may be familiar with is when you take the camera and you're in the airliner and you take a picture of what you see through the window. So you are used to this view. The next layer is the stratosphere. The stratosphere is much more dry than the troposphere. So within the stratosphere, you have high-speed airplanes, like for instance the Concorde or the SR-71, or all the X-planes, like the X-15, X-51A, the X-43, the Hi-Fire. And they all fly within the stratosphere because there the density has decayed by a lot already. The stratosphere also hosts clouds and those are called polar stratospheric clouds, and they only appear on the poles, and they are mostly composed of acid crystals and ice crystals. So those polar clouds, as I said, only appear in the both of the poles, and for missions involving hypersonic vehicles flying over the pole, that clearly will have an objective that is evident, but I'm going to leave to your imagination. There, for instance, atmospheric particulates, the effects of atmospheric particulates such as ice crystals on the hypersonic flight system would perhaps become important because of the reasons that we discussed in the last lecture. The stratosphere is also a layer that has a positive temperature gradient, and it is, as a result, fully stable. All the profiles that you see here in this plot are all fully stable, even though you probably know that when the temperature profile has a negative slope, if the slope is sufficiently negative, the system could become unstable because of buoyancy. So all these rates of variations are actually above that critical thermal rate variation. So all these layers actually are stable, as it couldn't be otherwise. The next layer, so before going to the next layer, let me just show you this picture. So this is a picture taken from an U-2 airplane in the stratosphere. And here, the pressure and density have already decayed to 10 to the minus 2 times the pressure and density at sea level. So these conditions in the stratosphere are very similar to, for instance, the conditions that you will find on the surface of Mars. The next layer is the mesosphere, that spans from 47 kilometers till 86 kilometers of altitude. The upper part of the mesosphere is already the boundary of the domain that we care for hypersonics. And the next layer is the thermosphere. So everything that happens above the mesosphere is highly dynamic and highly rarefied, and it is influenced by the solar radiation. So for instance, one picture taken from the mesosphere is in this Blue Origin mission with a dummy astronaut that you can see there, and this is the view from the capsule. Here the pressure and the density have already decayed to 10 to the minus 7 times the values at sea level. So this is a very unforgiving environment where you can already see the curvature of the Earth very clearly. Well, as I said, the temperature varies, but as you can see in the horizontal axis, it does not vary that much. So you have variations that go from 300 kelvins till almost 190 kelvins at the mesopause, but those variations are nowhere similar to the exponential variations of the density and the pressure. One important thing that I wanted to tell you about the variations in the thermosphere, you see that the temperature increases. It actually increases by a lot. But it is also true that the temperature in the thermosphere is so rarefied, the temperature there does not make too much physical sense, let's say, because there are not sufficient molecules to even define a temperature. In any case, when one plots the trajectories of hypersonic vehicles, like for instance here the Apollo, here you can see on the vertical axis the Reynolds number, and in the horizontal axis you can see the Mach number. And you can see that this curve that starts down there, close to Mach 27, right? And then it turns up, it goes around that elbow, and then it goes to the left. The reason for having that elbow there, that you see that the Mach number first decreases, is actually small, and then it increases, and then decreases. That may perhaps be counterintuitive with what we have learned before, that the that the Mach number and the velocity actually decreases through the atmosphere. The reason why that elbow is there, that you see an increment of the Mach number upon reentry, is because of the high temperatures in the thermosphere. So if one goes back to the definition of the Mach number, across the thermosphere, this speed of sound is going to be, is actually relatively large, because the temperature in the thermosphere, if you were just to define the Mach number based on that temperature, is large. As the altitude decreases, the temperature in the thermosphere decreases, and the Mach number increases, relatively speaking, right? So that's why you see first in that plot that had the Mach number here, that's why you see first an increment in the Mach number, and that's due to the decrease in the speed of sound through the atmosphere. The temperature there is still large, and then a nominal Mach number across the mesopause, that is the one that we have been always talking about. Let's say in the case of the Apollo, it was closer to 36. So remember that this part here is always because of the effect of the thermosphere. Well, these temperature variations actually do not translate that much into variations in the speed of sound within the layer that we care about, which is below the mesopause. So here I'm only plotting the altitude from 0 to almost 90 kilometers. So let's say that this is the layer, this is actually the portion of the atmosphere that we care about for hypersonics. You can see that the speed of sound is varying, but again, it's not varying as much as the density and the pressure. And particularly, it's actually varying even less than the temperature, because the speed of sound goes like the square root of the temperature. So if one looks, for instance, at that figure that you have there, so if one takes, for instance, the stratosphere, right? The stratosphere sees variations of the speed of sound from, let's say, 290, or let's say almost 300 meters per second, till 330 meters per second. So in other words, it sees variations of the speed of sound of the order of 30 meters per second across that entire layer. So if one goes back to the definition of the Mach number here, so one question is always, well, but the Mach number also has variations that are due to the variations in the speed of sound. Yes, there are variations of the speed of sound across the atmosphere, but these variations are not that large. As a matter of fact, if you take this and you calculate the variation in the Mach number associated to that variation in the speed of sound, so this will be equal to the Mach number multiplied by the variation of the speed of sound relative to itself. I'm just taking here variations in this equation. So this thing here, as I said, across the stratosphere varies as 0.30 meters per second over 300 meters per second. So this thing here is varying just by 10%. So I'm going to have variations of the Mach number with a frozen velocity. I will have variations of the Mach number only of 10% across the stratosphere. So the morale of this, if you go back to the screen, is that yes, across the stratosphere there are variations of the speed of sound, but if I take, for instance, 300 meters per second as a characteristic value of the speed of sound there, it doesn't really matter whether I take 300 or 290 or 310. So the Mach number is going to be mostly the same if the velocity of the hypersonic flight system is the same. So this is to say that in many of these conversations that we have in hypersonics, we always tend to give an estimate of the Mach number based on a characteristic speed of sound, and that characteristic speed of sound varies with altitude, but does not vary that much. So taking 300 meters per second does not lead to too much error in the estimation of the Mach number. Well, more frightening than the variations in the speed of sound are actually the variations in the kinematic viscosity. So here in the screen you have a plot with the altitude in the vertical axis and the kinematic viscosity in the horizontal axis. And again, this is the layer of the atmosphere that we care about. This is just from 0 to almost 90 kilometers. There in the screen you can see that the kinematic viscosity is actually changing by a factor of 10 to the 5. It's actually changing by a factor of 10 to the 5. So if we go here and then we recall that the kinematic viscosity is just mu divided by the density, of course, the density is varying exponentially. So this varies a lot, whereas this dynamic viscosity mu can generally be written as mu over mu naught being proportional to a power of the temperature, and this power of the temperature is about 0.75. So it varies even slower than the temperature. So most of the variation in the kinematic viscosity comes from the density. And there are variations of relative variations of the kinematic viscosity that are of the order of 10 to the 5 across the part of the atmosphere that we care for in hypersonics. So it is actually relevant in the following sense. So if we take here the again the surface of a planet, and this is the edge of space. Let's say that on the surface of a planet, I'm going to have, for instance, a sea level density, sea level pressure, sea level temperature, a sea level kinematic viscosity. From the conversation that we just had, we have learned that here at the edge of space, we go from these values to for instance, to a density which is 10 to the minus 5 times the density at sea level, to a pressure which is 10 to the minus 5 times the pressure at sea level, to a temperature that is going to vary, but not that much. So it's going to be just the sea level temperature and perhaps, let's say, minus 100 kelvins. And this variation is not monotonic, so it's going to be doing here wiggles and all of that. And then for the kinematic viscosity, we know that this kinematic viscosity here is going to be 10 to the 5 times larger than the kinematic viscosity on the surface. So these are the type of conditions that a hypersonic flight system needs to deal with. I don't know if you have ever heard about the challenges that the SR-71 had to go through when designing this airplane. It was called Blackbird 2. Many of the concerns when designing this airplane, which was a supersonic aircraft, was capable of reaching 3.3, Mach 3.3. So are still relatively small velocities, and it was flying all the time within the stratosphere. So one of the main concerns were the large variations in conditions that the SR-71 would have to withstand going from the tarmac to cruise flight in the stratosphere at 3.3. So, and those variations could be, for instance, in terms of temperature, in terms of stresses, and also in terms of environmental conditions. So you see that this problem here, the problem of going from the edge of space to the ground, is actually way much harder, because look at the variations that we have here in terms of environmental conditions. Those are huge. One important consequence of all of this is that if one has here a system, for instance, reentering, and this system has a length L, call it characteristic length L, then one could define a Reynolds number. Well, it is actually kind of difficult to define a unique Reynolds number for this system, right? That is reentering, because the system may be complex. Like, for instance, if we take here the and a hypersonic flight system like this, well, it is true that this thing has a characteristic length L, right? But it has more than one characteristic length, depending on the problem or depending on the region that we are interested in. For instance, here, close to the inlet, also a relevant length is the size of the inlet, right? For instance, here, close to the edge, a relevant size is the radius of curvature of the edge. So, and on top of that, there is also a Reynolds number that depends on the streamwise distance, for instance, along this surface. So this system has, could define multiple Reynolds numbers for this system. On top of that, there is also a shock wave here. So the free stream conditions are not going to be the same as the conditions downstream of the shock, or for instance, down here on the wake. But, in the realm of simplifying the discussion, one can always assign a characteristic Reynolds number to the system and try to obtain some first order conclusions of what will happen. So for instance, if I define here the Reynolds number, let's say at the entry interface, the Reynolds number based on L will be U infinity multiplied by L and divided by nu, right? So let's say that this thing is re-entering at speeds that are close to the first cosmic velocity, right? So U infinity will be perhaps close to the first cosmic velocity. So this is about 8 kilometers per second or so it was. So let's say that this is 8 kilometers per second for the velocity. Let's assume that this length is about 1 meter. So then I will have 8 multiplied by 10 to the 3 multiplied by 1, and here the kinematic viscosity, as I said, is 10 to the 5 times the one on the ground. So that is to say that the kinematic viscosity will be just 1 meter square per second. So this Reynolds number here is going to be of the order of 8 multiplied by 10 to the 3. So this is going to be of the order of 10 to the 4th. So I'm going to encounter Reynolds numbers of the order of 10 to the 4 up here when re-entering. And if I look near the ground, for instance, near the ground, this system, it depends on the mission, right? One may perhaps want to have a system that actually retains a lot of kinetic energy and hits the ground at high speed, or for instance, in the case of manned spacecraft, the re-entries actually finishes with 0 kinetic energy for obvious reasons. So let's say that near the ground, 10 kilometers of altitude or so, the velocity could be, for instance, Mach 1. So let's say that the velocity is 300 meters per second. Well, so if I construct here again the Reynolds number, so it's going to be 3 multiplied by 10 to the 2. Here I will have a 1 for the length. And here in the denominator, I'm going to have now the ground kinematic viscosity. So this is going to be 10 to the minus 5 meters squared per second. So this number here now gives me a number of 10 of the order of 10 to the 7. So you see that there is a variation of almost 10 to the 3 in the Reynolds number, right? So relative variations in the Reynolds number across the re-entry path, they are typically of order 10 to the 3, 10 to the 4. Well, this actually entails a complex problem because, as you may remember from your basic fluid mechanical classes, if you have a flat plate and the flow is incompressible, there is a boundary layer developing here, and that boundary layer at some distance x from the edge tends to transition, right? And can transition naturally, and this leads to turbulence here. Well, this critical x is typically defined as a Reynolds number based on x, which is just u infinity divided by infinity multiplied by x and divided by nu. this Reynolds number at transition tends to be of the order of 10 to the 5 to 10 to the 6. Those are typical streamwise Reynolds numbers leading to boundary layer transition. This is also equivalent to momentum Reynolds numbers of the order of a few hundreds, like 200 to 300. Those are the typical values for incompressible boundary layers. So here you can see that these numbers, unfortunately, 10 to the 4 and 10 to the 7, unfortunately in this planet, in the terrestrial atmosphere, these two numbers are located on each side of this limit. So that is to say that somewhere along the trajectory, somewhere along the reentry trajectory, I'm going to encounter a Reynolds number in the ballpark of transition. Well, this leads to the problem of boundary layer transition, which is a problem that has given a lot of years of research to industry, to academia, and to government labs to try to predict what happens in this scenario. And one could spend like several lectures explaining what happens in this scenario, and probably most likely one wouldn't learn much because the process is extremely complex, and sometimes very complex things escape or are beyond straightforward explanations, and therefore they become kind of tortuous and dense to try to make somebody understand the concept. So in this lecture, what I'm going to do is to try to show you a practical example where this problem becomes important, and that practical example is related to the Space Shuttle Endeavour. So probably you have seen the Space Shuttle landing many times in the news. As you know, the Space Shuttle was already decommissioned, but back in the 80s, during the first flights of the Space Shuttle, there were experiments trying to analyze boundary layer transition in flight. And one of those experiments is the one that you see in your screens. So this is a paper by Goodrich et al. From 1983, and what they did was to put thermocouples on the along the spine, on the underbelly of the shuttle, and then record the temperature traces during the flight. This was actually an actual reentry. So the results are shown here. Here in the vertical axis you have a Reynolds number that is based on the spine of the shuttle orbiter, which is about 35 meters. And in the horizontal axis you have the entry time. The total entry time for the space shuttle was around 30 minutes, which is those 1800 seconds that you have there. So you can see that at the beginning, right, the flow is laminar, and then it reaches a critical Reynolds number in the ballpark of a few millions, and then it transitions, and then it becomes turbulent. So the transition used to happen at after 1,000 times of starting the re-entry maneuver, and it lasted for about 300 seconds. So one perhaps more useful plot is this one that I'm going to show you next, that gives you the Mach number in the horizontal axis and the Reynolds number in the vertical axis. So here you can see the trajectory of a space shuttle in this two-dimensional space, and one can subdivide it into laminar flow during the first 1,000 seconds, then at Mach numbers of the order of 10, very close to 10, and at altitudes of 50 kilometers, this will happen. So at Mach 10, at an altitude of 50 kilometers, that will be the beginning of the transition period. And in the beginning of the transition period, what you have is that if this is the shuttle Here I'm seeing it from below, right? This is the underbelly. At high altitudes, the entire flow is laminar across this surface. But after approximately 1,000 seconds, at Mach numbers, the Mach number now has decreased to 10, and the altitude has decreased to 50 kilometers. Then one would start having here a transition front where the boundary layer will become turbulent downstream. As one decreases the altitude further, so the shuttle was penetrating into more dense layers of the atmosphere, then the Reynolds increases, and this front moves towards the aft of the, this front moves towards the fore of the space vehicle. So after some time, and as a matter of fact, after 300 seconds, this front moved close to the nose, leaving turbulent flow behind and laminar flow here. And this completion of transition happened at Mach 5 and at an altitude of about 40 kilometers. That you can see in the screen. So during that segment, the transition front will be moving across the along the underbelly of the shuttle. And then beyond that, one would obtain a turbulent flow over almost the entirety of a spacecraft. Well, it is important also to notice here that one is interested in the underbelly for obvious reasons, and it is that the shuttle used to re-enter, right, with an angle of attack that was almost 40 degrees. So obviously this is the surface that is of capital importance for calculating drag and calculating the heat fluxes. So just to summarize, transition would start at Mach 10 at an altitude of 50 kilometers, would last for 300 seconds, and would end near Mach 5 and at an altitude of 40 kilometers. So we are talking about transitional conditions that span 300 seconds, so those are 5 minutes, and 10 kilometers of altitude. So there's actually a very narrow zone of the total re-entry flight. But still, that process caused a little bit of concern. So let's see what is the footprint of that process. So here on the right, you have wall temperature time histories measured from the thermocouples that I was mentioning before. So in the first figure on the right, the upper figure, shows you the temperature trace near the forebody of a spacecraft. And you can see that the temperature increases. It increases to a peak value of 1,250 kelvins. And that increase is obviously due to a stagnation point heat flux, to the heat flux across the boundary layer, even if it is laminar, and that caused a lot of temperature increase in that part of a spacecraft. Then once that the peak heating passed, the temperature would decrease, and then you will see this little peak there that increases the temperature to 922 kelvins. Well, that's the signature of transition happening there. And then in the second panel, you can see something similar, but in the forebody, where you can see that the peak is actually much more pronounced. So those peaks are representative of transition. Well, one of the important things to notice here is that even though you have those peaks in the temperature profiles, the total amount of heat that was caused by transition was relatively small, right? So one always has to go back to the fact that there are two things that we are interested in. We are interested in the total amount of heat that is absorbed by the spacecraft, and in the heat flux. So boundary layer transition causes a very small increment in the total amount of heat that the spacecraft was absorbing. But on the other hand, would cause a large amount of local heat flux. And it is because across the front of transition, there is a large increase in the heat flux. It could be by a factor of 10, as I showed you in the last lecture with the reentry F experiments. Well, the physics of this process is kind of involved, right? So, for instance, if one plots here the streamwise coordinate x and here the Stanford number, or let's say the dimensionless heat flux, one would encounter that the dimensionless heat flux here would decrease, and then upon transition would increase, and depending on the method for transition, one will have a peak there or not. But the truth is that here there will be a jump in the heat flux that will be significant, and on top of that, this peak is moving along the underbelly. So that causes concerns in prediction, and this problem is still open. And it is also open because of the following. If one tries to do experiments of this process in a wind tunnel, and one has here the model of a space shuttle. Well, the wind tunnels are typically limited in what they can do. They are limited in terms of the Reynolds number. They are limited in terms of the Mach number. But they are also limited in terms of the stagnation enthalpies and in terms of the test times, the duration of the test time. Right? Those are limitations that all wind tunnels have when trying to address problems in hypersonics. But on top of that, on top of those limitations, there's also another limitation related to boundary layer transition. And it is that many of these wind tunnels, with very few exceptions, they have environmental noise, in the sense that here along the walls of the nozzle, right, and along the walls of the tunnel, there are boundary layers, and those boundary layers, what they do is to radiate. They radiate acoustic waves. And those acoustic waves, they interact with the boundary layer, overriding the test model. And as a result, that noise actually has an important effect on the outcome of the prediction. One of the discoveries that was done in that paper by Goodrich is that the wind tunnel measurements were always overestimating transition. So if in flight the front was there, the wind tunnel measurements will always give you an advanced front, and that is because the wind tunnel noise was triggering transition. So, for instance, in the next slide, you can see noise being generated from a hypersonic boundary layer. So here you have on the side here you have a gray scale map that shows you a pseudo-Schlieren plot of the density. So you see that in those gray corrugations, they are actually acoustic waves that are emanating from the eddies that are turning within the boundary layer and generating pressure fluctuations. So this is a Mach 6 hypersonic transitional boundary layer, which, by the way, since I'm talking about this here, let me just tell you that it was calculated with a code that is called the Hypersonics Task-Based Research Solver, HTR, that we published recently, that is available in the literature, and it is a very advanced code that is capable of running in GPUs, right? And it's capable of exploiting the most up-to-date government supercomputers, and that you can actually download for free. It's an open source code. It was actually written here in Stanford. So in the space shuttle, the transitional process that you saw was actually due to the tiles that you see in this picture. So if you ever go, for instance, to the Aerospace Museum in Washington, D.C., you're going to see tiles like this in the space shuttle there are many of these tiles protecting the underbelly of the space shuttle, and they are made of ceramic. So these tiles, they had to be pasted manually, and actually a little bit of imbalance or a lack of flash between these tiles, even by 1 millimeter, by just 1 millimeter, would cause here a disturbance that could lead to transition. And that actually was the process that triggered transition in the real flight of the space shuttle. There were actually experiments later to manipulate those tiles and study boundary layer transition, like these ones from NASA, in which one of those tiles was modified by adding a bump, like the one that you have on the left. And then the space shuttle will be recorded from the ground with an infrared camera. And you can see the signature of a bump on the wing of the space shuttle, like that yellow spot radiating more heat as a result of transition induced there by the bump. Well, boundary layer transition, as I said, is a very complex problem, and it makes it it's also complex because of the following reasons in hypersonics. If you look, for instance, at a nose cone, let's say, because of the curvature of this nose cone, there is going to be a positive, as a matter of fact, a negative. It is going to be a negative pressure gradient. So the pressure gradient is going to be favorable because of the curvature. Well, favorable pressure gradients, what they do is to stabilize the boundary layer. So this is the first thing that happens, is that because of the curvature, boundary layer transition is delayed. The second thing that happens is that these walls, they are typically cold. And cold in a sense that we are going to define in the next lecture, but cold means that the wall temperature is smaller than the stagnation temperature. So this coldness of the wall, what it does also is to stabilize the boundary layer. So that also prolongs the region of laminar flow along this cone. Third is that because of the shock wave that is produced here, one has an entropy layer here developing, as we discussed 2 lectures ago. This entropy layer has a vorticity, and it's an stabilizing vorticity. So because of this entropy layer, the boundary layer transition is also delayed. Then another thing that happens is that because of compressibility, there is an effect in the Mach number in the flow. Compressibility, as you know, it also involves acoustic radiation, involves transformation of kinetic energy into thermal energy, and what it does at the end is to delay transition in the following sense. Well, before I told you that there is an RE theta that one can reach that needs to be reached in compressible flows, that is of the order of 200 to 300 for transition. The criterion for compressible boundary layers is actually not this one, is that the Reynolds over the Mach number needs to be equal to this number. So that is to say that you actually need to reach RE theta values that are larger than this because of the effect of the Mach number. The fifth effect that plays a role here in boundary layer transition is a thermochemical effect. For instance, what happens when one has dissociation here or vibrational excitation? And that's not a well-known effect on transition that is actually currently very much under study. For instance, here in the screen you can see a calculation also carried out with the HTR code, where you can see a Mach 6 transitional boundary layer, and there what we're plotting is the isocontours of the Q criterion, but colored by the molar fraction of atomic oxygen. So this is a boundary layer in which we have air dissociation. So the effect of air dissociation is double. First, what it does, air dissociation is always an endothermic effect in the net. So what it's going to do is to drain energy from the flow. And then secondly, in order to treat dissociation, invariably one also needs to talk about or incorporate the effects of the temperature on the specific heat. Because if the gas is dissociating, of course, the gas is already vibrationally excited. So in this case, these calculations, for instance, they also incorporate, of course, the variations of the temperature, the variations of the specific heat with temperature. And those effects are also important because they also drain energy from the boundary layer. But these are advanced topics that are beyond the subject of this course, and probably maybe interesting for you to dig deeper in your own research or your own free time. Let's just go back here and tell you that not only the viscosity is important at high altitudes, there is also an effect related to altitude that has to do with rarefaction. So if one, for instance, has a molecule here, right? Let me just represent it as a sphere, like a hard sphere model. It's going to have a diameter d. So this molecule in the mean is going to be moving with a thermal mean speed, C infinity, and this thermal mean speed is the square root of 8 multiplied by Rg multiplied by T infinity and divided by pi. So this molecule is going to move some distance, right? Here, for instance. And during that motion, it may encounter another molecules. So in particular, we're interested in molecules that one could encounter within this sphere of influence that has a radius d. Why? Because any other molecule within this radius of influence is going to collide necessarily with this first molecule that we just drew here. So if one has many of these molecules around, for instance here, I draw here again the sphere of influence. Well, so if I have here a molecule, I encounter another one there, well, there is going to be a collision there, and then this first molecule is going to move again here somewhere. And then if I encounter another molecule there, boom, it's going to collide there and it's going to move somewhere else. So the question is, for instance, what is the volume swept by this sphere of influence per second before collision? So one can estimate that just by looking at the area of the cylinder, this area of the projected cylinder, multiplied by the thermal speed. So this will give me the volume swept per unit time by this molecule before colliding. And then if on top of that I multiply by the number density, that is to say the number of molecules within this cylindrical volume per unit volume, then this will be multiplied by n infinity. So this quantity here was actually units of 1 over second, because it has units of area, it has units of meters per second, and it has units of molecules, or in this time collision, per volume. So this defines a quantity that is 1 over second. So this quantity is actually called theta infinity and measures the collision frequency. One can derive a length from this collision frequency by saying that this length, lambda infinity, is equal to the mean thermal speed divided by that collision frequency. So this defines a quantity here, which is just 1 over pi b squared multiplied by n infinity, which actually requires here a prefactor. There is a prefactor here of the square root of 2 that I'm going to add here manually. And it is because this prefactor here of the square root of 2 is here because the derivation of this quantity that is called the mean free path is not as simple as what I'm attempting to do here on the board. It's actually a little bit more involved. And it requires consideration of relative motion between the molecules, and actually the relative mean velocity is the square root of 2 multiplied by the mean thermal velocity. So if you want to see more details about the derivation of this mean free path, I encourage you to look at the book by Vincenti and Kruger. There you will find a good derivation of the mean free path. But for now, let's work with this relation here of the mean free path. This n infinity can actually be written as the density rho infinity divided by the mass of the molecule. So it's just m divided by square root of 2 of pi multiplied by d squared and multiplied by rho infinity. If you evaluate this number at atmospheric conditions, for instance on the ground, where the temperature T infinity is 298 kelvins, the pressure P infinity just 1 atmosphere, the density is 1.2 kilograms per second, kilograms per meter cube. The diameter of this molecule you could approximate it as the diameter of a nitrogen molecule, for instance, that is tabulated. And I guess that's it. You wouldn't need anything else. Then and also you use the molecular weight for air, right, which is 29 grams per mole. The number that you would obtain here for the mean free path would be 60 nanometers. 60 nanometers. And the value of the collision frequency that you would obtain would be 10 to the 10 collisions per second. And the intermolecular distance that you would obtain, which you could approximate as n infinity to the minus 1/3, this intermolecular distance is about 3 nanometers. So this is the typical value of the mean free path, 60 nanometers that we have, for instance, in this room. So that means that every 60 nanometers on average, a molecule is actually colliding with another molecule of the gas. Well, the fact that this mean free path is inversely proportional to the density has strong implications for the purposes of our discussion. So if we come here, right, and we recall that the density varies exponentially with altitude, then we can do the following here. So then lambda, right, which is inversely proportional to the density, I know that lambda infinity at some altitude over lambda infinity at z equals 0. This obviously, because of this definition of the mean free path, is going to go like the density at sea level, right, divided by the density at whatever altitude I'm looking at. And this number is going to be equal to epsilon multiplied by, the exponential is going to be equal to the exponential of beta multiplied by z. So this is to say the following is that the mean free path actually increases exponentially with altitude at a rate that is also related to the scale height. So if we see this in the screen, here in the screen you have the altitude in kilometers and the mean free path in meters in the horizontal. And you can see that the mean free path actually increases by a lot within the layer that we are interested in for hypersonics. Well, if we go back here, right, there is a famous number that is called the Knudsen number. This Knudsen number is equal to the ratio of the mean free path divided by a characteristic length of the spacecraft. Well, I think if I already concluded that this mean free path increases with altitude exponentially, also the Knudsen number is going to increase exponentially with altitude. So one wonders, for instance, what's the typical altitude that one will have to achieve in order to have a totally rarefied flow? That obviously depends on the geometry, depends on L. So let's pick an L. In this case, we are going to pick an L corresponding to the radius of curvature of a space shuttle nose, which is about 1.2 meters. So there in the picture, you can see part of the thermal shield of the shuttle that protects the nose. And that's a thermal shield that is composed of a phenolic resin that is reinforced by carbon. So taking that 1.2 meters, right, one wonders, at what altitude do I get a Knudsen number that is equal to 1? Well, so the only thing that one needs to do here is to, again, substitute this relation there. So this will give me lambda 0, let's say lambda at the sea level, multiplied by the exponential of beta multiplied by z and divided by L, right? So this will give me just a Knudsen number at sea level multiplied by the exponential of beta multiplied by z. So let's say that I want a Knudsen number 1, right? I want a Knudsen number 1 to see at what altitude the flow will become rarefied. So if this is 1, right, the only thing that I need to do is to obtain here the critical altitude. This critical altitude is going to be 1 over beta multiplied by the logarithm of 1 over the Knudsen number at sea level. If you plug in this Knudsen number at sea level, the 60 nanometers for the mean free path at sea level and the 1.2 meters of the radius of the nose of the space shuttle, then you're going to find that the critical altitude is about 110 kilometers. So at 110 kilometers, the Knudsen number will be 1. So this is to say the following: if we look again at the screen, at 110 kilometers, the mean free path is of the same order as the radius of curvature of this geometry that you have in your screen. So you may be already kind of disappointed, because you will say, well, then the problem becomes almost impossible to treat, because if on top of that one has rarefaction, then what are we doing here? Well, one has to take into account the following, and it is that 110 kilometers is already very far away. So if one looks again at the surface, and here the edge of space is located at 90 kilometers or so. We are interested in this region here because this region has density, and the density is the one that brings the aerodynamics into the picture. And it is actually below this edge of space where there is a coordinate that we will be capable of calculating later, where the heat flux is maximum and where the deceleration is maximum. And there, where those two things happen, there is no rarefaction. Rarefaction only exists up here. And the estimate that I just gave you is actually a very conservative estimate. As a matter of fact, this estimate that I give you, this altitude that I give you, is actually pretty short, because in reality, the altitude at which the Knudsen number becomes 1 is actually higher than those 110 kilometers that I gave you. The reason is the following, and is that even though we have spent here some 10 to 15 minutes trying to derive this, it is true, and you probably agree with me, that if I have a gas like the one in this room, right, if I look at the molecules are colliding among themselves with a mean free path and with a collision frequency that is probably similar to the one that we have calculated here. However, if I were to take here, for instance, a metal plate, right, a big metal plate, I would move it towards the other corner of the room at Mach 20, you probably agree with me that there are going to be many more collisions against that surface, because the plate is actually moving really, really fast, and it's actually moving at speeds that are larger than the mean thermal speed. So that is to say that there is a correction that one needs to do to this mean free path that is related to the Mach number, and the effective mean free path is actually smaller than this lambda infinity that we have calculated with this simple theory, and it has a Mach number correction. I'm not going to go into the details of that, but I want you to be aware of that correction and of the fact that this derivation that we just made here is for a stationary gas that is basically not moving and is not colliding against any surface at very high speeds. So if you want more details, you can read a paper by Probstein that was published in 1961 in the American Rocket Society journal. Right, it is called Shockwave and Flow Field Development in Hypersonic Reentry. So this is a paper that explains this phenomenon of a mean free path in the presence of hypersonic flows. Let me just show you one last slide here, and it is that as one decreases the altitude of the object, right, as the object is penetrating in the atmosphere, the flow field is changing fundamentally. So here in the screen you have on the left a first stage in which the mean free path is actually much larger than the characteristic length of the object. That's a free molecule flow in which the molecules are just colliding like bullets against the surface. Then as the altitude decreases a little bit more, there are more molecules, right, because the density is starting to increase, and the molecules, they start bunching up in a layer that is lifted from the surface. So that's where the traffic jam starts to happen, and that's the first stage of a shockwave. There in that scenario, still the shockwave is very thick, and it can be as thick as the length of the object. The flow is still kind of rarefied. Then if one decreases the altitude even further, then the shock becomes thinner. In particular, the thickness of the shock becomes of the same order as the thickness of the shock layer. And one, for instance, could use the Navier-Stokes equations to calculate that flow subject to the free stream conditions. So that is to say that, for instance, the Rankine-Hugoniot jam conditions would not still apply across that very thick shock. Then if one decreases the altitude even further, then the shock becomes very thin, and it becomes much thinner in particular than the shock layer. But the flow is highly viscous. Remember that the viscosity has to do with altitude too, and one would require a fully viscous treatment of the problem. Then if one decreases the altitude even further, then the shock becomes much thinner than the shock standoff distance, and also much thinner than the boundary layer thickness, and that's a problem that enters in the continuum range. Before I finish, let me show you one thing, and it is that if one looks at the drag coefficient, one is used to calculate the drag coefficient either based on pressure, for instance based on wave drag, and also has a component related to friction. At high Mach numbers, right, and typical altitudes, this friction component is negligible. But it turns out to be that this friction component, if I, for instance, write it in terms of the friction coefficient is just mu multiplied by the velocity gradient at the wall divided by 1/2 the density of a free stream multiplied by the velocity of a free stream square. So here you can recognize that I have a density, I have viscosity, so I can actually express this as twice multiplied by nu divided by u infinity and multiplied by du dy at the wall. So in other words, the friction coefficient is proportional to the kinematic viscosity. As the altitude increases, the kinematic viscosity increases, and in this decomposition that you have here, the friction component may become of the same order as the wave drag. So I'll repeat it again. As the altitude increases, the kinematic viscosity increases. That increases the skin friction coefficient, and as a result, the friction component of the drag may become actually of the same order as the wave drag, right? And the wave drag coefficients that you have calculated in other lectures will have to be highly corrected by friction effects. Well, with this, we have finished this lecture. In the next discussion, we are going to be focusing on the structure of laminar boundary layers. I showed you during this lecture that a good portion of the reentry of a practical spacecraft, in particular more than 1,000 seconds, occur in laminar conditions. So in an escalation of difficulty, one should start studying laminar boundary layers, and that is what we will do in the next lecture.